Okay. Let me introduce. We're very happy to have Jae from MIT to tell us about quantum Steenrod operation on symplectic resolution.
Thank you for the introduction. Thank you again for the invitation to speak here. It's really a great honor to offer an opportunity to speak here at the seminar. Today, I'm going to tell you about this work that regards these operations from symplectic geometry called quantum Steenrod operations, which I would like to compute for these targets given by symplectic resolutions. So I consider this as sort of the first step towards a more involved research program where I would like to understand certain symplectic geometric Floer theoretic invariants for these class of target varieties given by symplectic resolutions. So this means I'm going to consider A model invariants which are defined from counts of, say, holomorphic curves inside these targets. In symplectic resolutions, those are a very fascinating class of target manifolds. So the definition is that you take some complex variety, this is smooth. This is called the symplectic resolution. If it's equipped with a holomorphic symplectic form. And such that it's a resolution of singularities of its affinization. So an example of something like this include interesting varieties such as cotangent bundles of flag varieties and Nakajima quiver varieties, things like this. And one simplest example that one can consider is something like a cotangent bundle of holomorphic cotangent bundle of the projected line. So this looks something like this. So it has base and it's the total space of the holomorphic cotangent bundle. So I have this belief that these class of varieties are very rich and interesting to study in the sense that a lot of these symplectic invariants, which are very difficult to compute in general, might be easier to compute for the symplectic resolutions coming from the rich inherent structure, geometric structures that these things have. And moreover, if one computes these symplectic invariants for these, one can hope for some kind of interpretation in terms of geometric representation theory, which is where these class of varieties originate from. So this is the long-term goal of understanding symplectic topology of these things that I'm interested in. And today I'm going to tell you about a rather surprising relationship between two objects in symplectic topology. One very classical and one more modern. And one of the objects, which is the more classical one that I'm going to focus on, is the quantum connection. In positive characteristic. So this is something that can be defined from the data of three-pointed Gromov-Witten invariants. So for every class in the second degree cohomology of my target manifold X, I get an operation that acts on the underlying vector space of the quantum cohomology ring. So I'm going to define these in more detail. but roughly maybe. So these are classical objects that can be defined just using ordinary Gorman-Witten theory, and they were of concern from the beginning of all this story. And I'm going to tell you a relationship between this operation and something more recently of interest in symplectic topology called the quantum Steenrod operations. So again, these are some kind of operations that are indexed, in this case, not only by second-degree cohomology classes, but any cohomology class target. And for some cohomology class like this, I'm going to define you an endomorphism, again, of the underlying vector space of quantum cohomology, which I'm calling the quantum Steenrod operations. There's some extra parameters that I'm going to explain. So these operations, which were defined by Fukaya in the late 90s as a deformation of the more classical Steenrod operations in algebraic topology, they were extensively studied by Nicholas Wilkins in recent years, and they have found many applications that today I might not go into, but many applications in Hamiltonian dynamics or arithmetic mirror symmetry, so mod P mirror symmetry. But in general, they are very hard to compute. Just like any of these types of symplectic invariants, which are defined in terms of counts of solutions to some generically perturbed PDEs. It's very hard to compute what the structure constants of operations like this are. But still, if you know something about them, you can say interesting stuff in symplectic topology. So
there is such a thing as arithmetic mirror symmetry?
So you can consider, so usually mirror symmetry is an equivalence between, say, homological formulation of the mirror symmetry would say like the Fukaya category on the A side is related to some kind of covariant shapes on the B side. And a feature of mirror symmetry is that the coefficients that you consider of the invariants that are defined on the A side. So for example, here the coefficients will be over FP. Those coefficients show up in the B side as the ring, the ground ring of definition of your varieties that show up in the B side. So arithmetic mirror symmetry would say that if you consider invariance, a topological invariance and positive characteristic on the A side, then on the B side you would get varieties over characteristic P. And then you can expect similar homological formulations like homological mirror symmetry or Hodge theoretic mirror symmetry and so on. So examples are studied by extensively.
It's very informal, interesting. I mean, it really is an
Yeah,
informal
yeah, yes. So please ask me a lot of questions. I don't guarantee that I'll be able to give good answers to all of them, but yeah, I'm happy to explain. So Seidel, I think this might be a paper from like 2019, studies these kind of arithmetic mirror symmetry, studies of Fukaya category with FP coefficients, and then computes some things about, I'm going to butcher this, but some kind of neighborhood of the identity endomorphism of the Fukaya category, and then formal group structures associated to that in characteristic P. And then he can use that to kind of guess what the mirror is on the B side, some kind of elliptic curve defined over FP. And there's some arithmetic way of guessing what the mirror is by just looking at the Fukaya category and over FP. So that's some new development, but I'm probably not going to do a good job of doing justice to it. But in that work also, this kind of quantum Steenrod operations show up. It's like the.
He was able to define define the category of equivariance that would be homological errors in the category?
On the B side,
Yeah.
yeah. So I think what he computes is like a very small part of the Fukaya category, like not the actual Fukaya category, but maybe some neighborhood of identity or something like this. Oops, sorry. And then
Things suggest that these things do exist.
these things do, yeah. There are suggestions that these things do exist, but very interesting to study, but there's not much study beyond.
Well, we understand homological nursing people are classes like the
Yeah. Yes.
So by what you're saying, what
Mhm.
constant characteristics.
That's right. And I should probably also mention there's work by Lekili and Polishuk that defines on the A side things defined over integers. So it's a very naive operation that you can do on the A side to just consider things over Z, but now on the mirror you suddenly get like varieties over Z, which is mixed characteristic and very complicated. So they do something like this for case of elliptic curves with punctures, maybe over Z. So there is some work towards arithmetic mirror symmetry in that sense. And these, all I want to say is that these are of interest to symplectic topologists, and but they're very hard to compute in general. So the upshot of today's work is that I'm going to explain a relationship. So there is a precise relationship between these two things, the quantum connection and the quantum Steenrod operations. And for practical purposes, for symplectic topologists, the outcome of this relationship would be a full computation of what these quantum Steenrod operations are, which are hard in general. So for symplectic resolutions. And from a more conceptual perspective, the relationship will give me a interpretation in terms of enumerative geometry of genus 0 holomorphic spheres, holomorphic curves, of this algebraic object called the p-curvature of the quantum connection. So the relationship that I'm going to tell you, it says that something called the p-curvature of the quantum connection in positive characteristic coincides with these quantum Steenrod operations. So this is an instance of this kind of general belief that I have that for symplectic resolutions, things are possibly easier to compute, and then maybe one can use that to understand things more generally about other symplectic manifolds. Okay, so I would like to begin by defining more carefully what this quantum connection in positive characteristic is and what the corresponding p-curvature of those connections mean. Is there any question that I can answer about the general direction that we're headed towards? Okay, if not, let me begin by talking slowly about this quantum connection. This is a rather classical object in symplectic topology and enumerative geometry of holomorphic curves. So today the version I'm going to use is that I'm going to fix a symplectic manifold, possibly with some nice positivity conditions to make the analysis easier. So you can think of either Fano projective variety or Calabi-Yau varieties. They can also be non-compact. And then I can define something called the Novikov ring, which for today we're going to work over Fp, which is the finite field of P elements. And these are generated by these exponential symbols indexed by the second degree homology classes of X. So this is called the Novikov ring. Now, from the data of this symplectic manifold, one can associate an invariant called the quantum cohomology. So this is a ring where the underlying vector space is just the singular cohomology of X with coefficients in this Novikov ring, but you have this different ring structure than the usual cup product. And this product structure is called the quantum product. It's defined as follows. So if you take two cohomology classes and you would like to compute their quantum product like this, the usual deal in symplectic geometry to define operations or algebraic structures like this, you're going to fix some basis of the underlying vector space that you're looking at, and then you write down any operation that you're interested in as an expansion in that basis. So I'm going to compute what this is in terms of some linear combinations of basis elements, where the structure constants are given by counts of holomorphic spheres. In this case, a three-pointed holomorphic sphere, where at the mark points, you have instance constraints given by the Poincare dual cycles of the cohomology classes involved. So this would look like this. And then you want to separate the counts by the degree of these holomorphic curves. And that's where the Novikov parameter shows up. So you look at these moduli space, you discretize that by looking at different homology classes, and then you isolate those counts by using this quantum parameter. Okay, so that's quantum cohomology, and it's a commutative associative product structure on this cohomology. And the quantum connection is defined from this data of quantum product. So here, if you fix a second degree cohomology class like this, this gives you a formal differentiation operator on the Novikov ring. So this lambda is this Novikov ring, where it acts on these symbols QA by some kind of a logarithmic derivative like this. So it acts on QA such that it spits back QA, but with this eigenvalue given by the intersection of a number of this second degree cohomology class with the second degree homology class. And then from this, you can define the quantum connection which is something like a formal connection that differentiates using this Novikov differentiation operator. And the connection matrix is exactly given by the action of the quantum product of this homology class. So, and this T here is some kind of a formal parameter of degree 2. So now this is a map from quantum cohomology, maybe with this extra parameter. There's a degree 2 map. So it's algebraically a simple thing. It's just some kind of differentiation operator. And the input of Flair theory that goes into defining this is relatively simple. It only uses the three-pointed Gromov-Witten invariance.
The basis that you picked,
yes.
Is there a result that says for change of basis, you get this thing?
Yes. So you can define so these structure constants are more information than actually computing this ring itself. So abstractly, this ring is well defined, but the structure constants will of course change drastically if you choose different basis elements. and it's sometimes easier to actually compute what this ring is abstractly in terms of generators and relations than to actually compute what the chromophotonic variance is. Yes, an important thing about this is like a flat connection in the sense that for different A and A prime, then these operations would commute. And that encodes the associativity and commutativity of this quantum product. So quantum connection is easy to define relatively. But it's very rich in the sense that a lot of interesting conjectures are there about this thing. And especially when you specialize to the case where your target symplectic manifold is a symplectic resolution, this is very well studied and it's also very interesting. So for X is symplectic resolution. So in a lot of cases, this comes with extra symmetry that I'll write like this. So usually there's some torus action of some torus A. Oh, I'm using the same notation there. Maybe I'll call this T. So usually there's some kind of torus action that preserves this holomorphic symplectic form and acts in a Hamiltonian way. And there's often it comes with some kind of a extra S1 action that scales this holomorphic form, holomorphic symplectic form. So in the case of T star P1, you have an action of S1 on the base P1, which extends to an action on the cotangent bundle. But there's also this action of S1 that scales the cotangent fibers of this holomorphic symplectic manifold. And that scales the holomorphic symplectic form, which in this case is given by the usual holomorphic version of the symplectic form that you get on any cotangent bundle. So it's the holomorphic ligable form. So these comes with so these kind of S1 dilation of the action that scales this holomorphic symplectic form, and it also comes with some kind of Hamiltonian torus action. And it's interesting to consider something like the equivariant cohomology of X with respect to these extra symmetries. And then you can also define equivariant versions of the quantum product taking into these kinds of extra symmetries in the definition of your chromowutin theory. So this is it's non-trivial. And for yes.
So do you ever use the symplectic form for one symplectic form?
So in this picture, those are extra structures that are handed to you. But the symplectic form that I'm using on the target to define these kind of symplectic invariants is not the holomorphic symplectic form. It's some kind of Kähler form that's compatible with the complex structure given on these varieties. That's actually very important. Yes.
Is it just like rotating the fibers?
Yes, rotating the fibers in examples like this cotangent bundle. And a lot of these examples of symplectic resolutions come from some version of cotangent bundle construction. So you can always think of it as some kind of a rotation of cotangent fibers, roughly.
Since you are talking about that, does it work generally for some cotangent bundle or just a complex manifold?
So you can definitely define these things as long as I think your base is maybe positive enough. Like you need some kind of nice conditions on the base that you want to take the cotangent bundle of to make sure that the analysis of defining these moduli spaces work.
So maybe two dimensions.
Yes.
It would be like SU2
Sorry.
in two dimensions, it would be like SU2
Yes, yeah. So I'm always going to just restrict on the maybe like the maximal torus inside kind of the group that you're considering, but definitely you can consider the full equivariant version. Was technically a little bit simpler to focus on the abelian action. And it's actually maybe a remark at this point is that working equivariantly, especially equivariantly with respect to that S1 over there, is essential to have some kind of non-trivial counts. So if you just consider the usual quantum product without this S1 equivariance, then the quantum product is going to be trivial. So it's actually essential that you consider S1 equivariantly. And from this data, you can also consider the corresponding quantum connection, which is defined in the exact same way. Instead of the quantum product, you just look at the equivariant quantum product like this. And it's a theorem of many people that these are very interesting to study for these kind of symplectic resolutions. So the first work, I think, is due to, sorry, maybe Okunkov Pandey. And there's also work by Braverman Maliko-Kunkov, also work by Maliko-Kunkov. That if you consider this quantum connection, equivariant quantum connection for symplectic resolutions, then they are often equivalent, gauge equivalent, to well-known connections in representation theory. So things like KZ connections, Casimir connections. I won't get into this, but the upshot is that if you consider basic symplectic invariants like the quantum cohomology and quantum connection for things like the cotangent bundle flag varieties or Nakajima quiver varieties, then for example, this quantum connection gives you back some kind of, it recovers and generalizations, recovers and generalizes some well-known objects in representation theory. So in that sense, it's rather interesting to study the symplectic topology of these varieties. Okay, so there are several remarkable properties that this satisfies for when you specialize to the case of symplectic resolutions. But one particular thing is that they are defined over the integers. And therefore, it's reasonable to consider the mod p reduction. You can do that. And so now you consider the same quantum connection in positive characteristics. Say you reduce to some kind of mod p coefficients for some prime p. Then you're given now with some kind of connection over mod p. And anytime you have a connection over mod p, you have something called a p-curvature. And the one that I'm going to care is the p-curvature of the equivariant quantum connection for conical symplectic resolutions. So what is this p-curvature? The thing to observe here is that derivations in positive characteristic, so this means p equals 0 for some prime p, has a natural pth power operation. So you start from some kind of operator like this, a partial derivative, and it satisfies the Leibniz rule, for example. Then in positive characteristic, so if this is a derivation, it satisfies the Leibniz rule. Then in positive characteristic, what happens is that the pth power of taking the derivations is also a derivation. So this is kind of surprising because you expect this to be something like a order p operator because you're differentiating p times. But nevertheless, you can check that this actually satisfies the Leibniz rule if you're working over p coefficients. So maybe I'll write it like this. So this is just composing this p times. So that's a new feature that happens if you're looking at derivatives in positive characteristic. And from this, you can define something called a p-curvature, which I'll denote by FA, like this, which is the difference between the pth power of the covariant derivative in that direction of the derivation. And the difference of that with the covariant derivative in the direction that's given by the pth power of that partial derivative. So this is the definition of a p-curvature. So you might be more familiar with the usual notion of curvature of any connection. So a usual curvature is, instead of being a one form like this, it's a two form. So if you have two directions, some vector fields x and y that you can differentiate things, then the usual curvature is the difference of the covariant derivative in those directions with the covariant derivative in the direction given by the Lie bracket of the two vector fields. So the curvature measures the failure of the covariant derivative of your connection to give you a map of Lie algebras from the vector fields to endomorphisms of your bundle. And in characteristic P, because the derivations are not only Lie algebras, but they have this p power operations as well, you can ask whether the covariant derivative preserves that p power operation as well. And that canonically gives you a notion of this kind of analogous notion of curvature. That's called the p-curvature. So in our case, when I am interested in this quantum connection, this p-curvature in the direction of A is just given by if you specialize this definition to the situation that we have, so when this is the equivariant quantum connection, this gives you an operation like this. So for every direction in H2, you'll get an operation like this, which again maps the underlying vector space of the quantum cohomology to itself, but now it's an operation of degree 2p instead of 2. And you have this extra parameters p to the p minus 1 showing up because our connection is really differentiating in like p del direction, not the del direction as the usual connection does. And now the question you can ask is like whether this algebraic thing has some kind of interpretation in terms of enumerative geometry, because everything that is involved in the definition is some kind of Gromov-Witten theory and some algebraic trick in positive characteristic. And the answer would be given in terms of these things, the quantum Steenrod operations. Okay, so this is all I want to talk about quantum connections. And yes.
Question, just referring to how can we get A on both sides? Why is the derivation to p power the same direction?
Yes, very great question. So in this case, my operator here was defined in terms of some kind of a logarithmic derivative like this. So in particular, it preserves this symbols itself. So if you apply this p times, what happens is just that you get p powers of this. But if you're working over mod p, then the p power of a number is the same thing as this number. Like that. So in this case, for this Novikov differentiation operator, you see that this p power is another derivation, and it's actually the same derivation that you started from. So that's why instead of having something like this, you get the same thing back again. Did that answer your question? Yeah. So I think the question was like, why do you have the same thing up here again? And this computation tells you that it should be the same. Okay. Now I would like to discuss about the quantum Steenrod operations, which are the main objects of my talk.
Just to clarify, the legal A, where is the leading?
A is some class of degree 2 in the singular cohomology of X. So it's not real kind of partial derivative in any geometric sense. It's just something formal defined in terms of this relationship. Okay, now let me discuss the quantum Steenrod operations. So when did I actually start? When oh, okay. I'll try to finish before 4. Okay, so what are quantum Steenrod operations? So I can give you the definition right away, but maybe it's more beneficial if I started from the properties of these operations that you might want to know about. So just like the quantum derivative, for which you have one operator for every class in H2, these operations are now indexed by cohomology classes in X, again with FP coefficients maybe. So every cohomology class, if you fix one, you get an operation called the quantum Steenrod operation, this which I'll denote by sigma b, where b is the cohomology class that I fixed. This is going to be an operation, again, on the mod p quantum cohomology, the underlying vector space of that. And then it's going to be a map of degree 2p, p times the degree of b of x p, together with extra parameters t and theta. So where do these parameters come from? Well, this is actually the group cohomology of the group, the cyclic group on p elements. If you work over fp coefficients. So that's the same thing as the equivariant cohomology of a point in fp coefficients. You can also think of this, if you're more topologically minded, it's the ordinary cohomology of the classifying space of the group V mod P in FP coefficients. So this is some kind of an infinite dimensional lens space with one cell of dimension I for every I. And if you work over, and those cells are cycles in FP coefficients, and in the end, if you try to compute the cellular cohomology of that infinite dimensional lens space, you get this power series ring in 2 commuting variables. This is for p greater than 2. So you have one generator in every degree, which is given by t to the I over 2 if I is even, and t to the I over 2 theta if I is odd. And I'll denote that unique generator in degree I by this notation t theta. Okay, so there are extra parameters showing up from a group cohomology of Z mod P, and in the definition of the quantum Steenrod operations, which I'll give later, that Z mod P group will show up naturally. Is there any question about this computation here? I can try to elaborate. Yeah, theta square. Yeah, so this is a graded commutative ring, and theta is an odd degree element. So if P is greater than equal to 2, then theta square will be 0. Yes, but yeah, and if P is equal to 2, then this is just the F2 cohomology of Rp infinity, and in this case, theta square will be equal to T. That's right. So you have an operation like this, and the properties that I want to emphasize here is first that this is a quantum deformation of Steenrod operations. So I'm going to define what these are. These are classical objects in algebraic topology, but just to first write down what I mean by this. If I take this operation and then specialize all the variables, the Novikov variables that keep track of the degree of my holomorphic spheres, if I set all of those to 0, so if I forget about all the contributions coming from non-constant spheres, then this operation is going to be given by taking the cup product with something called the total Steenrod power. Lost my chalk somewhere, but this is total Steenrod power. And how is this defined? So you have a map called the total Steenrod power from Fp coefficient singular cohomology of any space to the same cohomology but considered equivariantly. So I'll write it as a composition like this. Okay, let me explain. So the total Steenrod power is defined as a composition of two operations. The first one sends any cohomology class in Fp coefficient, and then it just clones it p times. So by Knuth formula, the ordinary cohomology of a p-fold product of x like this is just the p-fold tensor product of the same vector space, and then I'm just repeating the same cohomology class everywhere. And because this class is invariant under cyclic permutations, this actually lifts to a equivariant cohomology class with the group considered being Z mod P. And then you can pull this back by the diagonal embedding of x into the p-fold product of x. And this gives you the total Steenrod power. So this thing here, because if you look at the diagonally embedded x inside this p-fold product, that diagonal is the one that's fixed by these cyclic permutations. So this Z mod P actually acts trivially on this diagonal x. So this tells me that the total Steenrod power is going to be, by axioms of equivariant cohomology, this is again some power series in T and theta with coefficients in the cohomology of x. This is the construction of Steenrod operation, and it has many classical applications in algebraic topology, homotopy theory, and so on. But what I want to emphasize here is that there's these classical Steenrod operations which always exist for any FP coefficient cohomology that algebraic topologists care a lot about. But my quantum Steenrod operations, yet to be defined, is a quantum deformation of those in the same sense that the quantum product is a deformation of the classical coproduct. So if you forget, yeah.
It's literally the same. So like in the equivariant world, we have that, we have a classical multiplication and just the structure of multiplication by a coefficient ring comes from some relatives of Steenrod operations, like Cauchy dual. Should I think here that like you're trying to write Cauchy dual statement? For equivariant cohomology, you can consider it as a ring over the equivariant cohomology of the point.
Yes, yes.
But the Cauchy dual ring gives like the action by some sort of like Steenrod operation type of thing.
Yes, yes.
Symmetric.
Yes.
Should I think about this in the same sense here? You will try to construct some sort of Cauchy duality between quantum equivariant quantum cohomology and these operations?
So for classical cohomology, yes, this equivariant cohomology has this nice kind of causal duality relationship with the Steenrod algebra action. This sigma b, I'm going to define it just using symplectic geometry. So again, I'm going to look at some counts of holomorphic spheres.
Yeah, but by the end of the day, should they be Cauchy dual to each other, to the counts that we do for equivariant cohomology or the quantum connections or quantum cohomology?
Yeah, okay. I don't think I have a good answer to your question because I don't think I understand exactly how the Steenrod algebra acts on quantum cohomology. That's a homotopy theory question.
But it has like on equivariant cohomology. So what should I think about this as an upgrade, like both the form from classical world and it should still be Cauchy dual?
So I think I don't understand what the causal dual object should be in that picture. Okay. Maybe, yeah, sorry. I don't think I have a good answer to your question. I apologize. Yes. Is it possible to give some example for this classical Steenrod? Yes. So I'll give you an example that is going to show up again. So if you take a second degree cohomology class like this, then the Steenrod, total Steenrod power of a second degree cohomology class lies in H2P of X, like this. And in this case, you can actually show that this is always equal to the pth power of the cohomology class using coproduct minus tp minus 1 times b. So the Steenrod operation is going to be an expansion in terms of these t and theta variables with coefficients in cohomology. So the coefficient in front of 1 is just the p-fold power, and the coefficient in front of tp minus 1 is the identity, the cohomology class itself, and every intermediate thing that shows up are actually 0. So this is a computation for what this total Steenrod power is. Oh yes. It's okay. Yeah. I had yellow somewhere. Yes. Yes. So here, this is important. So going to show up again. So it's going to be BP minus TP minus 1 B. Like this. Yeah. Okay. So this is the quantum deformation of Steenrod operations. And it's also a deformation of the Steenrod power in the following sense. oh, sorry, I just said that. And it's also a deformation of p power in quantum cohomology. So if you set all these equivariant parameters coming from the Z mod p, and you set all of those to equal 0, then this is just recovering the p power in quantum cohomology. So it's simultaneously a quantum deformation of the Steenrod operations and a equivariant deformation of the p power operation in quantum cohomology. And another thing that I might want to say here is that if you compose two of these quantum Steenrod operations, and this is compatible with the quantum product in the sense that it's related to the quantum Steenrod operation on the quantum product of the two classes involved. Yeah, so those are some of the properties of these quantum Steenrod operations. And let me give you the definition in terms of counts of holomorphic curves. Are there any questions, further questions about? Okay. Now on to definition. So again, just like all of these symplectic geometric or flare theoretic invariants, I'm going to define this operation in terms of some expansion in a chosen basis of the underlying vector space of quantum cohomology. And the structure constants in that expansion are given by counts of certain J holomorphic curves inside my target. So in this case, it's given by counts of holomorphic maps from a copy of P1. So my curve here, C, the domain curve of my holomorphic maps, are going to look like this. So it's a copy of P1, and it has P plus 2 marked points along the curve. One is at 0, one is at infinity, and the other P marked points are along the roots of unity on the equator of this P1. So this is 1 e to the 2 pi I over P, and so on. So it's a P plus 2 marked curve. And how does Z mod P show up in this picture? Z mod P is a natural symmetry that you have on this domain curve of the holomorphic maps given by just rotation by one click. So I'm going to define an operation like that in terms of, again, in terms of some expansion in my cohomology class elements, the basis elements. And then I'm going to count holomorphic curves like this from this particular curve where I ask instance constraints along the input class and the output class at the two input mark point and the output mark point. And along the P fold roots of unity, these are supposed to pass through the instance constraints given by Poincare dual cycles to the class B that I'm fixing in the beginning. So everywhere along the roots of unity, I pair with this class B. And that's important to plug in the same classes here so that that's invariant under this rotation.
So the map itself is not a ZP invariant?
The map itself is actually not ZP invariant because, yeah, I'm going to get to that point very soon. Yeah, so again, you separate these counts by homology classes. So this A is like the degree of your holomorphic curve. Okay, now you want to count this moduli space up to this Z mod P symmetry. And the issue with the analysis is that you want to define this moduli space, and you want it to have some kind of Z mod P action inherited from the Z mod P action on the source of your holomorphic map. But this is in general impossible because so this is a map from C to X that satisfies some kind of J holomorphic curve equation. But you can't actually do J holomorphic curve equation to make sure that these counts are counts of smooth manifolds. You want the moduli spaces to be transversal, and then you need to introduce some kind of perturbation to your equation like this. And it is generally impossible to choose this perturbation data to be invariant under the Z mod P action. So instead of, this is a little bit of technical wrinkle that shows up in this kind of symplectic geometry way of defining this, but you have to deal with that. And maybe I'll only say that the way to deal with that is to do some kind of parametrized Flare theory. Where instead of trying to fix a perturbation data that's regular and Z mod P invariant, you look at families of perturbation data parametrized over something like BZ mod P, and then you separate the counts from different cells in that parametrizing space using these equivariant parameters. So it's just going to be some expansion in terms of cohomology and these quantum parameters and the equivariant parameters. And the counts are given by some kind of solutions to parametrized equations parametrized by the perturbation. Okay, maybe that's all I want to say about the Flare theory that goes into making sure that these counts are well defined. That's some issue in analysis. But now the question is how to compute these, because
Can you explain a little more what you, so you say conscious move to be ZP invariant? Is that what you do?
yeah, so okay, yeah. Yeah, so the issue is the following. So I want this number to be well defined. So what I need to show is that the moduli space of solutions to an equation like this is a compact smooth manifold of dimension 0. Then I can define this count as a cardinality of that connected components of that manifold. But the issue is I want to achieve that this thing is smooth, and it's in general, it's not possible to choose this new that is in a way that's Z mod P invariant, so that this moduli space actually has a Z mod P symmetry inherited from the symmetry of the domain curve. So instead what I do is I let my perturbation data to be parametrized over BZ mod P. So now I count pairs of my curve with some chosen parameter here. And this is a union of one cell in each dimension. So now the ith equivariant moduli space that shows up as the structure constant is the counts of some curves like this where W is asked to lie in delta I. Does that answer your question? So this is what I mean by parametrized Flare theory. I want my perturbation data to be parametrized over this classifying space. And it's like an analytic incarnation of the idea that you want to take something like a derived quotient of this moduli space. Well, anyways, okay, so now a crucial thing that allows some partial computation of these operations is the following compatibility relation of these operations with the quantum connection. So So another important property of these quantum Steenrod operations is that it commutes with the quantum connection in positive characteristic. And this can be used to compute sigma b partially. So this relation is not enough to constrain my operation sigma b enough so that it actually is determined, but maybe you can determine the counts for the cases where the degree of the homomorphic curve is small. So it gives you some kind of partial computation. Right, and the question is, so this relation with the compatibility relation with the quantum connection basically gave all the computations that we know, all partial computations that we know about these quantum Steenrod operations. And the question was whether one can go beyond the scope of this flatness relation. So this says that sigma b is covariantly constant. And one can ask whether you can compute more, maybe using something other than this relation. So that's where I thought maybe it could be interesting to try to compute these for symplectic resolutions, because then you have a bunch more structure on your target variety. And then maybe you can use this to determine what sigma b is. So what I started was to try to compute these sigma b for the simplest symplectic resolution, which is this T star P1 that I introduced earlier. There I used some kind of very explicit geometric considerations about the situation in hand to actually determine all the structure constants of the sigma b. So that was very kind of direct geometric proof, and it wasn't geometric computation, and it wasn't clear how to generalize this. But once you have answers, then you can start observing things about the answer that you have and try to prove more structural results using that as a stepping stone. So that leads to the main result of today. So I'm writing this up. So the relation is that if X is some nice enough conical symplectic resolution, so here nice enough, I mean something like this. Fixed points of the Hamiltonian torus is discrete. Then I can show that this, if you choose some kind of second degree cohomology class, so that both the quantum derivative and the quantum Steenrod operations are well defined as operations of degree 2p, then this difference between the two operations is actually nilpotent. And moreover, if you know that the quantum product has a distinct eigenvalues, so simplest spectrum, then you can show that for these conical symplectic resolutions, that the p-curvature of the quantum connection and the quantum Steenrod operations are actually the same. They coincide. So p-curvature is quantum Steenrod. Yeah. Maybe I should have mentioned that again, these kind of target spaces have a lot of these extra torus equivariants, and everything up here can be generalized to the case where you have these kind of target equivariants. So instead of just saying quantum cohomology of X, I can say T cross S1 equivariant quantum cohomology of X. And then I can define equivariant generalizations of quantum Steenrod operations. I can prove equivariant versions of this covariant constants relation. And for that, I can prove the relation like this. Okay. So you can read this in two ways in the following sense, that this quantum Steenrod, which is something generally pretty hard to compute, that in these nice cases, they're essentially determined just from the data of equivariant Gromov-Witten theory of symplectic resolution, which is much less data than trying to compute something like this. And it's also giving you some kind of interpretation of what this p-curvature of the quantum connection is in terms of actual operation defined in terms of holomorphic spheres. Okay, so in the remaining time, I would like to introduce some of the ingredients that go into this proof and how, for example, these conditions like symplectic resolution with this symmetry is being used. But are there any questions I can answer about the statement of the result? Yeah.
So away from degree 2, was like the highest Steenrod operations for H4, for example?
Yeah, so definitely they can be defined, but the difficulty is that you don't have a definition of what the p-curvature is unless you're second degree homology class. But you also have a relation of this form that, it's just get covered, but like the composition of quantum Steenrod operations is the same as the quantum operation on the quantum cohomology. So if you know that your quantum cohomology is generated by degree 2 classes, for example, then this determines everything for sigma b for degree 2 classes, and that relation will determine everything for any quantum cohomology class. And in a lot of these examples of symplectic resolutions, it's actually the case that the quantum cohomology is generated in degree 2. So you can also think of it as a full computation. Thank you.
So the number 3 property was that it's algebra homomorphism?
Yeah, it's a homomorphism. It's an algebra homomorphism from quantum cohomology to the endomorphism ring of the underlying vector space of quantum cohomology. Okay, any other questions? Great. Okay, so the proof uses,
Do you have a description?
Sorry.
Image of this sigma.
I don't have a good.
It's like it's a definition.
Yes, so I was actually talking with Ishan earlier about this kind of story about Frobenius constant quantizations, but it's a little bit more speculative, so maybe I don't want to talk over a record. But I think there's a natural characterization of what the action of the quantum Steenrod operation is, but it's a little bit more speculative, and I didn't think too much about it. So okay. So now the key ingredient that goes into the proof is extra operators that exist for these symplectic resolutions, or in general, target symplectic manifolds with a lot of symmetry, like this. In this case, we have T plus S1. And for target manifolds like this, you have an action of what's called the shift operators. And these show up as an important ingredient in a proof of something like this. So what are the shift operators? So now suppose you have an action of some group like this, say abelian action on your X. So suppose they act in a Hamiltonian way. Then, for each choice of co-character, S1, so there is a, right, so S1 scales the holomorphic symplectic form. But if you look at the Kähler form, which is invariant under that S1 action, it's actually S Hamiltonian for that one. Yeah, it doesn't act Hamiltonian for the holomorphic symplectic form. Yeah, that's right. Yeah. So for each co-character from S1 into this group that acts on X, you get an operator called the shift operator. So these are maps, which I'll denote by this bold-faced S of sigma, which again maps from quantum underlying vector space of quantum cohomology, the equivariant version, to quantum cohomology. And maybe I want these parameters as well. And these are defined from counts of holomorphic sections of a particular Hamiltonian fibration. So you're going to count sections of some fibration over P1 associated to your choice of co-character where the fiber is given by X. So how is this fibration defined? Well, you take 2 copies of the 2-disk times your symplectic manifold X, and then you glue them using this loop, the S1 loop inside the Hamiltonian diffeomorphisms of X to glue 2 copies of this. So you use sigma, which is some map now from S1 into the Hamiltonian diffeomorphisms. You use that as a clutching function to define this total space of the Hamiltonian fibration. So at every point, you have this fiber given by X. And then one can, again, do something like this. You can count holomorphic sections of this fibration, and then that defines you a map from the quantum cohomology of the 0 fiber, which is X, to the quantum cohomology of the infinity fiber, which is again X. So it gives you a map. So yes.
You need to add p coefficient?
This can be defined over the integers. Yeah, and in particular, you can reduce to FP. A little t is again this kind of, right, you can think of it as just formal parameter. It also shows up in this picture as the S1 or Z mod P equivariant parameter for the action on the base, like this. Which is like the loop rotation. Yes, so a key fact about this vibration, E sigma, is that you have an action, you have action of T cross S1, which is acts fiberwise, and it also has an action of another S1, which I call the loop S1, which is lifts the S1 action that you have on the base of the vibration, which is given by rotating. And the thing to observe is that S1 loop acts trivially on the 0 fiber, but it acts by non-trivially. It acts exactly by the sigma on the infinity fiber. So in particular, what this implies, if you chase down the definition, is that these shift operators are not linear over the full equivariant cohomology ring. Instead, if you have, so if I call the equivariant parameter of this by z, say, and maybe you have these extra equivariant parameters coming from this t. We'll call them lambda. Then this actually shifts the equivariant parameters. So instead of being linear over all of these equivariant parameters, it changes as you commute things against this shift operator. So it shifts equivariant parameters. And they define what's called a compatible difference connection. To the quantum differential equation. So those are extra structures that you have in this story. So the theorem about these shift operators is that they are compatible with the quantum connection again. So if you look at the quantum connection and then you try to commute that against the shift operators, then they commute up to this shift that's always present in this story. I think this is due to maybe originally to Kunkov and Pandey in their study of these shift operators. And one can also show that these quantum Steenrod operations also satisfy the same relation. So there are compatible with the shift operators as well. So this theorem here is telling you that the quantum connection and the difference connection defined by these shift operators are compatible to each other. And this theorem here says that just like the quantum Steenrod operations were compatible with a differential connection by the theorem of Seidel and Wilkins, it's also compatible with these difference connections defined by these shift operators. So in that sense, it's kind of a partner theorem to Seidel and Wilkins, which says that the quantum Steenrod operations commute with the quantum connection. So this is proved by a familiar argument in symplectic geometry that uses some kind of degeneration of holomorphic curves. So the proof is relatively standard, but what's more interesting is the implications of a relation like this. So that you can ask, like, okay, how strong is this as a constraint on the quantum Steenrod operations? How strongly does this constrain sigma b? And the answer, which is given by this theorem, is that it constrains a lot. So it almost essentially determines it. Okay. So any questions about these shift operators before I quickly sketch the proof of the main result? Yeah.
I was trying to be thinking about these shift operators in reference to the Steenrod operations, because at P1 you do looks like you have the Z actually kind of the same way that, I don't know, it feels like these are very similar, but it's hard to say how.
That's right. So the viewpoint that I'm trying to advertise here, which is invisible from the presentation that I gave because I streamlined things to be defined that way, is that the Z mod P action that shows up in the definition of quantum Steenrod operations, I'm thinking of that as you just observed, as part of this kind of loop rotation on the domain. The original definition of quantum Steenrod operations used by this Fukaya and Wilkins and so on uses the permutation action on the mark points to define these quantum Steenrod operations. But the viewpoint that I'm trying to promote here is that instead of considering the action that shuffles the mark points on your domain sphere, you should really think of this Z mod P action as the one that rotates. It's a part of this S1 action. And then relations like this come out more naturally. Just because, as you notice, it's like part of the same action, geometrically. Yes, but I didn't give the definition of quantum Steenrod operation in terms of shuffling the mark points, so that's why that shift of viewpoint is a little bit invisible here. Yeah, thanks. Are there any other questions? Yeah, okay. So now, roughly, the proof of the main theorem goes like this. So once you have a relation like this, you can say the following thing. So now you want to fix this class. You want to consider the p-curvature and the quantum Steenrod operation. Proof of main theorem. And then you want to choose a nice homogeneous basis of the cohomology. And for conical symplectic resolutions, these kind of nice basis of cohomology is, okay, not use blue. These nice basis is given by the theory of stable envelopes. So homological stable envelopes give you a very good set, natural set of geometric basis elements of the cohomology ring, that equivariant cohomology ring, sorry, that lives in the same dimension if your fixed points are actually discrete, finitely many points. So if you are looking at these two operations in that basis, you can try to expand these in terms of equivariant parameters. So this Z was the equivariant parameter of the S1 dilation of the holomorphic symplectic form. And I'm going to expand this in terms of as polynomials in Z. So something linear in T and lambda, P1. So something of degree P in T and lambda FBP, like this. So now each of these FB0s, FB1s, and so on are just matrices of numbers. And all of the cohomological degrees, so both of these are degree 2p operations, all of those cohomology degree is represented by these equivariant parameters, which are of degree 2p. And you can do the same thing here. Now the upshot is the following. So the first is that the leading asymptotics of the two operations in these expansions are the same. So this follows from the fact that so this follows from the fact that if you just turn off all the equivariant parameters to 0, then these are just both given by p-fold power of the quantum product. So everything here is, yeah.
So without p equal to 0,
Yeah, so FB is an operation on quantum cohomology. So it's I can represent in this basis by some kind of matrix, right? So the entries of that matrix is going to be degree 2p polynomials in these variables z, lambda, t, and so on. Yeah, and then I'm just expanding, like I'm writing down that matrix in terms of sums of matrices.
So this what's contained in the coefficient of p0, p, are the pure.
Yeah, they're pure numbers, but they're also dependent on q. So there are some power series in q with coefficients in it. Yeah. And you also have this relation that not only their leading asymptotics agree, their constant terms also agree. So this has to do with the fact that this both of these limits, when I turn off the z parameter, is the same as the cup product with the total Steenrod power on B, which I previously computed as this expression. And both of them are compatible with the shift operators. So everything up here is just using formal properties about quantum Steenrod operations. And this new intertwining relation with the shift operators. Oh. And then once you have that, you can show that the difference has to be a nilpotent endomorphism by just taking the difference and then computing its characteristic polynomial. So now you want to look at characteristic polynomial of the difference of these two matrices. So you can just expand this out like this. It's like some polynomial in this formal variable. Now these coefficients the first condition here tells you that this degree in Z is bounded by I times p minus 1. Because you don't have any Z to the p terms. The difference is the highest order of Z that shows up is p minus 1. So if you take I to the exterior power, the degree is bounded like that. And also, so this expression is also divisible by Z to the I because, well, their constant terms agree. So if you take the difference, everything is divisible by Z. And then if you look at the I to the exterior power, it's divisible by Z to the I. And the third relation, if you take the shift operator in the direction of the S1 action that scales the holomorphic symplectic form, this tells you that it's not only divisible by Z, but if it's divisible by Z, then it's also divisible by the thing that gets after shift. So it's also divisible by Z plus T. It's also divisible by Z plus 2T, and so on. Like this. And this is something of degree bigger than the one that I had up there. So that's a contradiction unless this thing is 0. So only by using this formal properties of the quantum Steenrod operations and the p-curvature with this new relation with the shift operators, I can show that this thing is actually a nilpotent operator. So I'm almost done. So this shows the first part of the statement. Oh. And now for the second part of the statement, I'm going to use this upcoming result in representation theory due to Etingof and Varchenko, that if the quantum product has distinct eigenvalues, then the p-curvature in that direction also has distinct eigenvalues. This is a paraphrase of their upcoming statement. So what does this tell you? Well, if the quantum product has distinct eigenvalues, then the p-curvature also has distinct eigenvalues. Now we know that the quantum Steenrod operation commutes with the p-curvature because it commutes with the connection. And their difference is nilpotent. So they're simultaneously diagonalizable, but if FB had simple spectrum and their difference is nilpotent, then this actually tells you that they are the same operation. In this case. And now this thing is known for many conical symplectic resolutions, because we understand their quantum cohomology pretty well. So this is known for cotangent bundle of flag varieties, partial flag varieties, quiver varieties of type A, and also known for, say, Hilbert scheme of points on a plane. So for a large class of, I mean, large depends on your viewpoint, but for many of well-known symplectic resolutions, we know that this thing holds, and therefore we know by this implication that the p-curvature and the quantum Steenrod actually agree for all of these examples. So let me just end by venturing some conjecture. So now the proof uses things about conical symplectic resolutions and the quantum product having simple spectrum. But one can ask whether this relation holds in general, even for, say, compact, so closed symplectic manifolds, which are Fano, for example. Their quantum connection is much more, arguably much more interesting. And if one can show something like this in general for any quantum connection and quantum Steenrod operation defined for, say, Fano targets, that would also be something interesting. So I think I'll stop there, and thank you again for the invitation.
Question about like connection to 3D mirror symmetry.
Mm-hmm.
And something that can say how does this operation, shape operator, this is what the space we're acting on.
Right. So okay, this is venturing into area that I'm less familiar with, but right. So several things can be said here, I think. One is that this action of shift operators on quantum cohomology, they can be interpreted in terms of the action of the Coulomb branch on quantum cohomology. So that's one thing that shows up in this 3D mirror symmetry story. So now I focused on the case where the action on the target is abelian, some product of tori, and in that case, the the Coulomb branch, pure Coulomb branch, is given by lattice of co-characters. So So for each co-character, I defined you a shift operator, but there's a generalized version of that where you can just write down an action of the actual Coulomb branch algebra of the quantum homology. So that's one way it makes connections with some characters that show up in 3D mirror symmetry story. Maybe another one, which is less of 3D mirror symmetry, but maybe equivariant 2D mirror symmetry, is that these quantum Steenrod operations can be shown to annihilate certain flat sections of the quantum connection that is constructed by Varchenko. So what Varchenko does is that for these kind of quantum connections, and a particular specialization of this parameter given by the specialization of the ratio of the two equivariant parameters that showed up in our picture. So this is the one S1 parameter for the loop rotation. Sorry, this is the loop rotation, and this is the one that scales the holomorphic symplectic form. And for each specialization of that ratio, he constructs a flat section to this quantum connection. So it's annihilated by this. And now you look at the quantum Steenrod operation. Now those are covariantly constant endomorphisms of the quantum connection. So this is the specialization again. So nabla again depends on Z and T. So I want to specialize this parameter like this. Yeah. So Varchenko constructs these kind of flat sections, and because the quantum Steenrod operation commutes with nabla, you can try to ask the question, well, how would quantum Steenrod operations act on these solutions? Because they preserve the space of solutions. And what can be shown is that quantum Steenrod operation actually annihilates these solutions that Varchenko constructs. And that was also a hint towards expecting something like this, because the work of Etingof Varchenko also shows that the p-curvature also annihilates these kind of solutions. So that was a hint towards guessing something like this should be true. And these solutions are obtained from mirror symmetry, so to speak. It's given by some integrals of potentials. Yeah, so those are two partial answers that I can give.
In Files, categories over FP, that's a pretty simple operation, right? You just decide to work over FP coefficients, so that's it.
Yes. Yeah.
So in some sense, you solve the theory first, and then you try to specialize the coefficients. So it has.
Yeah, but